Hello everyone, I'm Alimadadi, and today I'm honored to present Waverunner, an elegant approach to hardware acceleration of state machine replication. This work has been done with collaboration of Hieu, Shenghsun, and our advisor Mike Ferdman, Peter Miller, and Shuai. The distributed protocols are at the center of many critical systems such as cloud infrastructure and large-scale distributed databases. And in these systems, protocol handling incur a massive performance overhead, such that on the network side, other than network communication, the messages must cross PCIe and reach software. And on the software side, other than application execution, CPU must parse, process, and generate packets. Hardware accelerators are one of the many ways to gain the high performance, and they achieve high throughput with minimal latency. However, they pose a major programmability challenges that every change requires a massive effort and time to develop hardware. So our goal is to deliver hardware accelerator performance and software flexibility. Two of the existing approaches to the challenges we said in previous slide are either leave implementation in software and minimize the overhead, or move everything to the hardware and pay the programmability cost. We saw an opportunity in the middle ground that we propose an approach in hybrid hardware software that leaves all the complexity in software and design in a way that move only the simplest and performance critical operation in hardware. Our Waverunner prototype accelerates the graph protocol and application like memcache and move only the most common function to the hardware in 200 lines of code. It achieves 100 gigabit line rate at 1.8 tail latency. With our approach, Waverunner delivers hardware speed with mostly unmodified software. For the rest of this talk, I'm gonna discuss the distributed protocol performance challenges and the ways to overcome them. And later, I'm going to introduce the Waverunner and how we solve the performance challenges. And later, we go over the results of Waverunner in different scenarios, and at the end, conclusion. So in traditional software, clients send a message to the server, and server, after process them, respond to client. And this creates one round-trip NIC CPU communication. However, in distributed protocols, things is a little bit different, as the leader has to copy the request to the replica and wait for its response. And this adds extra round trips. These round trips shows in two forms of overhead: one, network communication overhead, and PCIe traversal. The modern network equipments are fast, and their latency are not so bad. However, the PCIe traversal are costly, and they add a large amount of CPU work. This overhead reduce the performance of system in overall in terms of throughput and latency. Throughput drops because CPU become busy processing packet, and PCI crossing and software interaction adds latency. There has been an extensive amount of work to overcome the performance challenges we set. On one side, we have kernel bypass method that passes data directly from NIC to application memory, like in DPDK and RDMA, and they improve the throughput and latency considerably. However, the CPU still is the bottleneck for processing all of the distributed protocol packets. On the other side, of the spectrum, we have the FPGA hardware that re-implement entire network layer distributed protocol and application in hardware, and they achieve line rate throughput with minimal latency. However, the FPGA hardware development is notoriously difficult for both evolve and debug. For example, any changes in the hardware takes several hours to build compared to the software that compilation takes a couple of minutes. So we saw an opportunity that makes us divide the distributed protocol in two parts. The complex software that contains a majority of code and they run too rarely that impact the performance. And the other ones are the simple common routines that contain only 10% of RAF code, and optimizing their performance can optimize the overall system's performance. We built the Waverunner accelerator based on our observation and moved the only repetitive common cases to the hardware. That gives us maximum throughput, minimum latency, and more importantly, it frees up the CPU cycles for the application. And any deviation from the common cases go to the software. For example, the Waverunner accelerator passes all the unknown messages to the software, and if it detects failure, it let the software handle them. So with our approach, Waverunner makes the common case fast and uncommon case correct. So let's go more into detail of how we designed Waverunner, both in hardware and later see how our software interacts with the accelerator. Waverunner hardware is based on conventional NIC, and it adds 3 RAF-specific hardware. The packet filter parses the messages and identifies RAF packets and tell the protocol handler to process them. Protocol handler contains the RAF logic for handling client requests and follower messages on leader and leader requests on follower. And protocol handler uses packet generator to send messages to the other replicas. The protocol handler contains the core of the RAF logic, and it's only written in 200 lines of C++ code that can be translated to hardware with HLS tools. On the software side, Waverunner operates in full software and accelerated mode. In full software mode, Waverunner runs as if it doesn't have any acceleration and executes all of the RAF functionality. And in accelerated mode, Waverunner calls the application handler when it receives the commit message from the accelerator. And if on the accelerated mode, it detects any failure, it turns off the acceleration, switch to full software mode until it reaches the stable state, and then it turns on the acceleration. We also integrated Waverunner with real-world applications such as Memcache, Redis, and simple key-value hash. For these applications, the Waverunner forwards the messages directly to the application without kernel involvement, similar to DPDK. So let's see how Waverunner works in general. In our experiment setup, we have our servers and clients are connected to a switch with 100 gig link NIC. We have 3 Linux server, each with U280 Xilinx FPGA with 200 gig port. And in order to compare Waverunner with software approaches, we used 100 gig NICs Mellanox NIC. We also have 8 client hosts, each with 225 gig Mellanox NIC. And on our clients, we send messages in open loop to push the leader as far as possible with minimum size request. We use 32 bytes of payload as a minimum size request throughout our experiment, and we perform no batching at client to simulate their real workloads. First, we experimented on Waverunner on its own without attaching it to the software to evaluate the raw power of the Waverunner. We measured the replication latency as a function of throughput. In our experiment, the replication latency represents the time that the leader gets the request from the client until it gets the majority of the responses from the followers and commits it. And we push the throughput as far as we don't experiment any packet loss. In order to compare Waverunner with software approaches, we developed RAF on top of DPDK that's shown in different shades of orange. And our RAF DPDK is able to achieve up to 5 million packets per second for small packets. And its replication latency goes from near 5 microsecond to 5.7 microsecond. We also experimented on Hieu, an state-of-art software approach that has the best replication latency known to us. And it gets the impressive replication latency of 2.3 microsecond that is barely above the network latency, and it is increasing up to 4.2 microsecond, near 5 million packets per second. In comparison, the Waverunner that is shown in blue can achieve the network saturation at 26 million packets per second. And more importantly, its median and tail latency become constant and identical at 1.8 microsecond. Now, we attach the Waverunner to the application to see how it works. We use 3 applications: key value hash that is shown in gray to represent what happens if our application has low overhead, and memcache and Redis for their widely used in different scenarios. And we increase the number of server threads to scale the throughput of the application. The key value hash, as we see, can achieve almost the line rate with 32 server threads. And memcache and Redis are able to get 20 million packets per second. That is 14 times higher than when they are not attached to the Waverunner. For the last experiment, we measured the end-to-end latency on the client side, and we compared the memcache and Redis with the original version of them. In our graph, in order to see how the packet size affects the latency, we increase it from 8 to 1 kilobyte. And the error bar shows the 99th percentile tail latency. So the original memcache and Redis can achieve more than 40 microseconds with wide range of tail latency. And in compared to that, Waverunner can achieve less than 12.5 microseconds, which is 3.5 times better than the original application. So in conclusion, We discussed that distributed protocol handle a massive performance overhead and in software implementation are too slow and hardware implementation of too inflexible. We proposed a middle ground in terms of Waverunner and hybrid hardware-software approach, and it handles a simple common operations in hardware and leave everything else in software. Waverunner runs RAF protocol with minimum size packet, and it achieves line rate of 100 gigabit per second with constant tail latency, and it only uses 200 lines of C++ hardware code. Thank you, everyone.